All right, let's talk about the invisible force that's powering literally everything around you right now. Current electricity. It's this silent, steady flow that lights up our world. But honestly, how does it really work? Well, we're about to find out.
Okay, let's start with a puzzle you've probably seen a million times. A bird, just chilling on a high-voltage power line. That wire is carrying thousands of volts, right? Enough to be incredibly dangerous for us. So how does the bird get away with it? Why no zap? Just keep that question in the back of your mind for a bit.
And here's puzzle number 2. You've got this tiny, super simple thing called a fuse inside a lot of your expensive electronics. Its only job is to destroy itself. So how does this one little component manage to sacrifice itself to save your whole system from a massive power surge? By the time we're done here, you'll know the answer to both of these.
To crack these mysteries, we need a toolkit. And when it comes to electricity, that toolkit really just boils down to 3 key ideas. You've got the flow, you've got the push, and you've got the friction that tries to stop it all. Let's break them down.
First up is electric current, which we represent with the letter I. The easiest way to think about this is just like water flowing in a river. It's the amount of electric charge that's moving past a certain point. It's the what that's actually flowing.
And here's where it gets kinda wild. The sheer range of this electrical flow in the world, and even inside our own bodies, is just staggering. On the really tiny end of the scale, you've got microamperes. We're talking millionths of an amp. These are the super delicate electrical signals that your brain is using this very second to process my voice. It's amazing.
Then you've got the everyday stuff. The lamp in your room, your TV. Chances are it's using a current of around 1 ampere. This is like the workhorse level of electricity that runs our homes. And then you have the other extreme, a single bolt of lightning that can unleash a current of 10,000 amperes or more. I mean, that is a truly terrifying amount of charge moving all at once.
So all these charges are moving, but they don't just decide to get up and go on their own. Something has to give them a push. Let's take a look at the force behind that flow.
Right, so what's the engine here? What's driving this whole electrical river? What gives these little charges the motivation to start flowing in one direction?
They need a push. It's as simple as that. Just like water needs pressure to flow through a garden hose, electric charges need a kind of electrical pressure. The official term for it is potential difference, but you and I know it by a much more common name, voltage. And this push comes from places you see all the time. The batteries in your TV remote, those little cells you put in a wall clock, and of course the gigantic power generators at a power plant. They're all designed to do just one thing, provide a nice, steady voltage to get that current moving.
Now the journey for these charges is, well, it's not exactly a wide open highway. There's always something getting in the way. It's time to meet the resistance.
If you could shrink down, like way down, and watch a single electron trying to move through a wire, you'd see it's basically playing a game of pinball. It's constantly bumping and crashing into the atoms that make up the wire itself. It's chaotic.
And this constant opposition, this sort of electrical friction, has a name. It's called resistance. We measure it in a unit called ohms. Literally everything has some resistance. It's just a basic property of stuff.
So let's recap. We have the push, which is voltage. We have the flow, which is current. And we have the obstacle, which is resistance. And as it turns out, these 3 things are all tied together by one beautifully simple rule.
We have to go all the way back to 1828. A German physicist named Georg Simon Ohm figured it all out. He uncovered the single most important relationship for understanding basic circuits, and, well, they named it after him. And what he discovered is so intuitive, it makes sense. If you increase the push, the voltage, you're going to get more flow, more current. It's like turning up the tap on a hose. But if you increase the obstacle, the resistance, the flow gets smaller, just like pinching that hose. It's really that simple. And this all gets wrapped up in one of the most famous formulas in physics. V equals I times R. Voltage equals current times resistance. With this one little equation, you can figure out exactly what's going on in a simple circuit. This is Ohm's law, and it is the absolute foundation of electronics. Okay, so we've got the push, the flow, the obstacle, and the rule that connects them all. Now we know the rules of the game. But so what? How do we actually use this invisible journey to do something useful for us? So here's a little puzzle for you. Individual electrons in a wire actually drift along incredibly slowly. I'm talking slower than a snail.
So how is it that a light bulb, maybe hundreds of miles away from the power plant, turns on the very instant you flip the switch?
Here's the trick. It's not about one electron making the entire journey. The wire is already jam-packed with electrons. The signal to move, the electric field, is what travels at nearly the speed of light. Go back to that hose analogy. If the hose is already full of water, the instant you turn on the tap, water shoots out the other end, right? It's the same idea.
And hey, remember all those little collisions that cause resistance? Turns out they're not just a bug, they're a feature. Every time an electron bumps into an atom, it gives off a little bit of energy. That energy comes out as heat. And if you make the wire really, really thin, like the filament in an old light bulb, it gets so hot that it glows. That's how we turn electricity into light.
All right, it's go time. We have our toolkit, current, voltage, and resistance. And we have our master key, Ohm's law. So let's put it all to work and finally figure out what is going on with those birds and those fuses.
First, let's zoom in on a really important clue, heat. You've all felt your phone charger get warm, right? Well, that's because as the current is flowing, those electrons are constantly colliding with atoms inside the wire. Each little collision creates a tiny vibration, and billions of these vibrations are what we feel as heat.
This effect is called Joule's heating. And the power that's lost as heat follows this formula, P equals I squared times R. Now, the most important part of that formula is that the current, I, is squared. That's a huge deal. It means if you double the current, you don't get double the heat, you get 4 times the heat. So the big takeaway is, high current means a ton of heat.
And this explains exactly how a fuse works. When a power surge happens, the current, I, goes through the roof. Because of that I-squared relationship, this generates an insane amount of heat almost instantly. The little wire inside the fuse is designed with a really low melting point. It gets so hot, so fast, that it just melts, breaking the circuit and stopping that killer current dead in its tracks. And just like that, Mystery 1 is solved.
Now what about the bird? Okay, remember, current needs a potential difference, a push to get it to flow. Since both of the bird's feet are on the exact same wire, they're at almost the exact same high voltage. There's no significant voltage difference from one foot to the other. And if we look at Ohm's law, V equals IR. If your voltage difference, V, is basically 0, then the current, I, flowing through the bird has to be basically 0 too. It's not the high voltage that's dangerous, it's the current that flows because of a voltage difference.
This stuff explains other everyday things too. Ever wonder why a really long extension cord might not power something as well? It's because resistance is proportional to length. A longer wire means a longer path, which means more atoms for the electrons to bump into. That equals higher total resistance. And as Ohm's law tells us, if the voltage from the wall is constant and you increase the resistance, the current has to go down.
So far, everything we've talked about treats wires like simple pipes that follow Ohm's law perfectly. But the world of modern electronics, the chips inside your phone, is built on materials that kind of play by their own set of rules.
Yeah, the circuits inside our computers aren't made of simple copper wire. They rely on these amazing materials called semiconductors. And the fascinating thing about them is that the resistance isn't a fixed value. It can change based on things like how much voltage you apply. They don't have that nice simple linear relationship that Ohm's law describes.
So here's the key difference. For an ohmic conductor, like a copper wire, if you graph voltage versus current, you get a nice straight line. Double the push, you double the flow. But for non-ohmic devices like transistors and diodes, that relationship is nonlinear. A tiny little change in voltage can suddenly cause a massive change in current. And it's this unique behavior that lets them act as the microscopic switches that power all of our modern gadgets.
Okay, we've gone from simple wires all the way to complex microchips, so let's just take a moment to boil it all down to the most important takeaways. So, we did it. Our mysteries are solved. Fuses work because of Joule's heating, that P equals I squared R formula. High current creates massive heat and the fuse melts. Birds are safe because there's no voltage difference across them, which means no current can flow. And this is also why we transmit power over long distances at super high voltage. It minimizes the current, which massively reduces the energy loss to heat in those long wires. If you're going to remember anything from this, remember this right here. Current is the flow. Voltage is the push. Resistance is the opposition trying to stop it. And the golden rule, V equals IR, is the simple little law that connects them all. Which leaves us with one final thought. We have seen how a single, simple law can govern what happens in a piece of wire. But how do you go from that to a smartphone, where billions of those non-ohmic transistors are working together in perfect harmony to create magic? Well, That is a story for another time. Thanks for watching.